There's exactly one federal seismometer at the California volcano that just produced 208 earthquakes in 5 days. 3 GPS receivers, no gas monitoring, no tilt meters. Last week, that volcano, silent for 40,000 years with confirmed magma underneath it, shook harder than it has all year, and the official alert level never moved off normal. By the end of this, you'll know whether that was the right call, and what the forewarning signs are that nobody is currently positioned to catch. Between last Thursday and midday yesterday, the United States Geological Survey catalogued 208 earthquakes beneath the Coso Volcanic Field in Inyo County, California. Almost all of them came from a single cluster about 10 kilometers east-northeast of Coso Junction, at an average depth of roughly 2.5 to 3 kilometers. The largest was a moment magnitude 3.96, a number that rounds in every practical sense to a magnitude 4, and it struck at 59 minutes and 55 seconds past midnight Pacific time on Sunday morning. Coso is not a mountain, which is part of why most people have never heard of it. It is a scatter of 38 rhyolite lava domes, cinder cones, lava flows, hot springs, and fumaroles spread across about 400 square kilometers on the eastern flank of the Sierra Nevada, at the northern edge of the Mojave Desert. It sits roughly 160 kilometers northeast of Bakersfield and about 64 kilometers north of Ridgecrest. Most of it lies inside the boundary of Naval Air Weapons Station China Lake, which means most of it is closed to the public. The last confirmed eruption at Coso happened about 40,000 years ago. That was the Volcano Peak basaltic cinder cone and the lava flow that came with it. Beneath the center of the field, geophysical and geochemical studies have detected a zone of partially molten rock. Actual magma, confirmed, not inferred. The California Volcano Observatory lists Coso as one of only 7 volcanoes in California with molten rock underneath it. So the setup is straightforward to state. A volcano with confirmed magma under it, quiet for 400 centuries, produced more than 200 earthquakes in 5 days, including one that shook hard enough to be felt in the surrounding valleys. And through all of it, the official alert level for Coso never moved off normal, the aviation color code never moved off green, and no public statement about the activity was ever issued. Not one. That silence is the story. Not because it's wrong. And I want to be clear about that from the start, because by the end of this, you're going to see that the science behind that silence is unusually solid. The silence matters because of what it reveals about how thinly this particular volcano is watched, and about the difference between a system that has looked at the data and concluded there's no threat, and a system that doesn't have the instruments to tell you either way. The shape of this swarm is the first thing that doesn't behave the way it's supposed to. Earthquake sequences that follow a big shock decay in a very specific, very predictable way. It's called a Mori decay, and it has been understood for more than a century. The rate of aftershocks falls off roughly as the inverse of the time elapsed since the main shock. Fast at first, then slower still, always downward. It is one of the most reliable patterns in all of seismology. Coso did not do that. Last Thursday produced 16 catalogued events. Friday jumped to 52. Then Saturday collapsed to 9, a drop of more than 80%, back down near the ordinary background rate for that patch of desert. Anyone watching the catalog on Saturday evening would have reasonably concluded the episode was over. Sunday produced 116 earthquakes. That is more than double the peak of the first pulse. And every one of the swarm's 4 largest earthquakes arrived inside that second surge. There is no main shock in this sequence. The biggest event did not come first and get followed by a fading tail of aftershocks. The magnitudes climbed with time. 1.93, then 2.98, then 3.29, then 3.96, with the largest arriving 72 hours after the sequence began. That progression is the textbook definition of a swarm rather than a main shock and aftershock sequence, and it means something specific about the physics. A decaying aftershock sequence is a single stress release relaxing. A swarm that stops and restarts larger is a driven process. Something is applying stress repeatedly in pulses, rather than one thing having broken and the crust settling afterward. The largest earthquake struck at 7:59 and 55.920 seconds, universal time on Sunday, the 23rd of August, which is 59 minutes and 55 seconds past midnight Pacific Daylight Time. Its depth was 2.83 kilometers. Its final reviewed moment magnitude was 3.96, computed from 40 stations, with an azimuthal gap of 35 degrees and a location error of 0.18 seconds. The depth uncertainty is plus or minus 0.47 kilometers. The horizontal uncertainty is plus or minus 0.16 kilometers. Those are tight numbers. 80 seconds later, a magnitude 3.36 struck at 2.55 kilometers depth. 77 minutes after that, a moment magnitude 3.51 struck at 2.78 kilometers. 3 of the 4 largest earthquakes recorded in the Coso Volcanic Field this entire year happened inside a 78-minute window in the middle of Sunday night. To put that against the year's baseline, from the 1st of January through the 20th of August, nearly 8 months, that same search radius produced exactly 2 earthquakes of magnitude 3 or greater. In 5 days, it produced 4. The swarm doubled the year's entire magnitude 3 count in less than a week. Across the first 19 days of August, the area was running about 5 earthquakes a day. During the swarm, it ran at roughly 42 a day. On Sunday alone, it ran at about 23 times the early August rate. There is one detail about that magnitude 4 event that has already produced a viral claim, and it's worth 30 seconds. The earthquake was first issued as a magnitude 4.1, then revised down to 3.9, then settled at a value that rounds to 4.0. Online, that sequence became evidence of a cover-up. It isn't, and the direction gives it away. A cover-up revises the number down and leaves it down. This one went down and then back up. More decisively, the type of magnitude changed along the way. The early numbers were local magnitude, computed from the amplitude of ground motion on whichever instruments reported first. The final published number is a moment magnitude, computed from the actual seismic moment of the rupture using 40 stations. Those are 2 different physical quantities measured 2 different ways. Expecting them to match is like expecting a car's speedometer and its fuel gauge to agree. And the corrected figure was published, time-stamped, and left in the public catalog with its full revision history attached, which is a strange way to hide something. The geometry of this swarm is the part almost nobody has reported, and it is the part that matters most. Every significant earthquake in this sequence falls between 36.061 and 36.070 degrees north latitude, and between 117.8375 and 117.8442 degrees west longitude. In plain terms, that is a box roughly 1 kilometer north to south by 600 meters east to west. 208 earthquakes over 5 days came out of a patch of crust smaller than a large airport. The depths are just as confined. Setting aside 2 unrelated background events near Ridgecrest, every catalogued earthquake in the cluster falls between 2.26 and 3.51 kilometers depth, and the clear majority sit between 2.5 and 2.8 kilometers. That is a range of a little over 1 kilometer, top to bottom, across 200 events. Now hold on to one number from that, because the whole interpretation turns on it. Nothing in the catalog shows the earthquakes getting shallower over time. The shallowest event in the sequence arrived yesterday morning at 2.26 kilometers. But there's no trend, no steady upward migration, no front working its way toward the surface. That absence is not a small detail. When magma or magmatic fluid rises through the crust, it cracks rock ahead of itself, and the earthquakes it produces climb. You see the hypocenters shallowing week over week. That is the single clearest seismic fingerprint of magma on the move, and it is not present here. Here is where the title question gets its answer, and the answer has 2 halves. The first half is that the California Volcano Observatory has a documented, published process for exactly this situation, and by that process, this swarm did not qualify. The observatory's own explainer lays out a 4-step triage. Which stations does the signal appear on? What are the depth, the location, and the character of the signal? Is it sharp and distinct, which means rock breaking, or broad and wobbly, which means water or steam moving through a crack? Then the 3rd step, which is the one that decides, what do the other data streams say? In the observatory's own words, magma pushing into the subsurface has to displace the rocks around it and will cause deformation. The gases that come with it want to rise and eventually have to come out somewhere. If neither of those things shows up, the source either isn't magmatic or isn't going anywhere. At COSO, neither of those things showed up. There is no reported ground deformation associated with this swarm. There are no reported long-period earthquakes. The broad, wobbly signals that indicate fluid or magma moving. There is no reported harmonic tremor, and there is no reported change at the fumaroles. The observatory's threshold for escalation is also on the record. Before an alert level ever changes, the first move is to talk to partner agencies and issue an information statement, a public heads-up that something is being watched. That did not happen. The most recent COSO-specific notice on file dates from July of 2019, after the Ridgecrest earthquakes, and its conclusion then was that the swarm was tectonic, not volcanic. So on the science, the silence holds up. And it gets stronger when you look at where these earthquakes actually are. Multiple independent studies have tried to locate the magma beneath Coso, and they disagree with each other, which, as it happens, is useful. A study from 1980 found a low-velocity body between 10 and 17 kilometers down. A study from 2003 inferred a shallow reservoir at roughly 5 kilometers, with a discontinuity near 15. Work published in 2005 and 2007 described a tabular, sill-shaped magma body 20 kilometers long and 3 to 5 kilometers thick, sitting between 11 and 16 kilometers. Seismic tomography published in 2022, using more than 137,000 travel time pics, imaged a low-velocity body between 5 and 20 kilometers. Every single one of those estimates is farther down than this swarm. The shallowest credible top of the magma reservoir is about 5 kilometers. The earthquakes are at 2.5 to 3. There is a minimum of 2 kilometers of solid rock between the shaking and the melt. And that rock is not ordinary rock. Beneath the Coso geothermal field, the brittle to ductile transition, the depth at which rock stops cracking and starts flowing under stress, is bowed upward to roughly 4 to 5 kilometers. Regionally, that boundary sits near 11 kilometers. At Coso, the hot crust has pushed it more than halfway to the surface. That has two consequences, and both cut the same way. First, the earthquakes physically cannot be much lower than they are, because below that boundary, rock deforms by flowing rather than breaking, and flowing rock does not produce catalogued earthquakes. Second, pressure changes in a shallow, brittle fracture network do not propagate meaningfully across that boundary. The seismicity is mechanically walled off from the magma underneath it. That is the strongest single piece of evidence in this entire story, and it points away from an eruption, not toward one. Which raises the obvious question. If it isn't magma, what is applying stress to that 1 kilometer box of rock over and over in pulses? There is an industrial scale answer sitting directly on top of the earthquakes, and it has been running since 1987. The Coso geothermal field is one of the larger geothermal operations in the United States. 4 power blocks house 930 megawatt turbine generator sets for a rated capacity of 270 megawatts. A gathering system connects more than 140 wells across nearly 15,000 acres. The operator currently lists 99 production wells and 35 injection wells. Reservoir temperatures run from 200 to 328 degrees Celsius. Mass flow exceeds 14 million pounds of fluid per hour. Now look at the well depths. Those production wells run from 2,500 feet to more than 13,000 feet, which is roughly 0.75 to 4 kilometers. The entire earthquake swarm, top to bottom, sits inside that interval. The seismicity, the brine, the steam, and the re-injected water are all happening in the same slab of rock. This is not a fringe connection. It is established in the peer-reviewed literature for this specific field by name. In 2021, a paper in the journal Nature examined why Coso produced almost no aftershocks after the magnitude 7.1 Ridgecrest earthquake. When the stress changes said it should have, the authors found that 30 years of geothermal heat production had depleted the shear stress inside the reservoir. And in the course of establishing that, they stated something else plainly. Thermal contraction of the reservoir initially induced substantial seismicity at Coso. Pull heat out of rock, the rock shrinks, shrinking rock cracks. That is a published, non-controversial, peer-reviewed mechanism operating at this exact location. Then, in February of this year, a second paper went considerably further. Published in Scientific Reports, it analyzed 15 years of local seismic data, alongside daily operational records from the field. The authors found a strong correlation between short-term increases in the earthquake rate and seasonal changes in both the volume and the temperature of the fluid being pumped back into the ground. During peak injection of colder fluid, the seismic response was near instantaneous, measurable up to 2 kilometers away from the injection well, and far too fast to be explained by pressure diffusing through pore spaces in the rock. Read that against the shape of this swarm, a driven process applying stress in pulses, a response that switches on, switches off, and switches back on harder. A source volume locked inside 1 kilometer of crust and 1 kilometer of depth, a depth band that matches the wells. That is not proof. Nobody outside the operator has the injection records for last week, and I'm not going to pretend otherwise. But of the available explanations, it is the one that accounts for the 2-pulse structure, the extreme confinement, and the location, all at once. One more piece of context makes the picture sharper. The field's output has roughly halved over its lifetime, from 270 megawatts rated and about 302 at peak, down to roughly 145 megawatts today. That decline is the signature of a body of rock that has been substantially cooled over 39 years of extraction. Meanwhile, the ground itself has been sinking, not swelling. Satellite radar from the 1990s measured subsidence across about 50 square kilometers at up to 3.5 centimeters a year. More recent measurements put maximum subsidence at up to 15 millimeters a year. For as long as anyone has been able to measure it, COSO has been going down. Volcanoes, preparing to erupt, go up. So the science holds, and here is the second half of the answer, the half that should still bother you. There is one seismometer operated by the Geological Survey near the Coso Volcanic Field. It was installed in 2001. There are 3 continuous GPS receivers making up the deformation monitoring network. They went in 2000, 2005, and 2006. There is no gas monitoring at COSO. There are no tilt meters. There are no strain meters. Compare that to Long Valley Caldera, about 200 kilometers north, 46 GPS receivers, and 9 tilt meters. Now go back into the observatory's own decision process. The third step, the one that actually discriminates between magma and everything else, depends on deformation and gas. At COSO, deformation is measured by 3 receivers, and gas is not measured at all. The instrument that would catch the strongest early warning sign, a bulge in the ground surface, exists in triplicate across 400 square kilometers. There is a partial answer to this, and it's an important one. The dense local network at COSO is run by the Navy's Geothermal Program Office, using downhole and surface seismometers, and it is genuinely good. It resolves earthquakes down to magnitude minus 0.5 and records several hundred events a month in one flank of the field alone. Which means the number 208 is not the number of earthquakes at COSO last week. It is the number the public network could resolve. The real figure is almost certainly an order of magnitude higher. That finer catalog exists. It just isn't public. And there is a defensible reason the federal monitoring is thin. The threat ranking is not a popularity contest. It is a 24-criterion assessment combining hazard factors with exposure factors. COSO scores 55 and ranks 72nd out of 161 American volcanoes in the moderate band. The population within 10 kilometers of the field is 370 people. Within 100 kilometers, it is just under 72,000. COSO is monitored roughly in proportion to what it can actually do to people. The Geological Survey has published what an eruption at COSO would look like, and more usefully, what would come before one. The language is specific. Earthquakes would precede any eruption. Weeks to months of heightened earthquake activity and ground deformation would probably precede a future eruption. Because the region is geothermally active, an eruption would likely begin with a series of low-level steam blasts. Read that carefully, because the distinction carries the whole story. Earthquakes preceding an eruption is a necessary condition, not a sufficient one. The stated precursor package is weeks to months of elevated seismicity plus ground deformation. 5 days of shallow shaking with no deformation signal is not that package. It isn't close to that package. And for scale, this swarm is not even the biggest thing COSO has done recently. In July of 2019, after Ridgecrest, the field was producing roughly 600 magnitude 1 or greater earthquakes per day. About 1,600 events in the 2 days after the 8th of July, 12 of which reached magnitude 3, with the 2 largest at magnitude 4.1. Last week's swarm ran at about 1/15 of that daily rate, and its largest event was slightly smaller than those 2. 7 years on, COSO is doing a much smaller version of what it did then, and nothing about the intervening period suggests a buildup. 4 things would change this assessment, and all 4 are worth knowing. The first is deformation. If those 3 GPS receivers start showing inflation instead of the long-running subsidence, that is the signal that matters more than any earthquake count. The second is a change in the character of the earthquakes, a shift from sharp, distinct rock-breaking signals to the broad, wobbly, long-period events that indicate fluid or magma moving, or the onset of continuous harmonic tremor. Both of those preceded the 1980 eruption at Mount St. Helens by months. The third is upward migration, hypocenters climbing week over week rather than sitting in the same 1-kilometer box. The fourth is any change at the fumaroles and hot springs, new vents, hotter output, stronger gas emission. And there is a fifth, which is procedural rather than physical. If the California Volcano Observatory issues an information statement about COSO, that is, the system telling you it has moved from watching to concerned. It has not done that. When it does, it will be public and it will come before any alert level change. For now, the honest summary is this. The swarm was real, it was unusual in shape, and it was almost certainly not magmatic. The earthquakes are 2 kilometers above the shallowest possible magma, on the wrong side of a boundary that shallow pressure changes cannot cross, inside the depth interval, where an industrial operation has been pulling heat out of the rock for 39 years. The alert level stayed at normal because the data supports normal. But the reason that answer is worth stating out loud, rather than assuming, is that at COSO, the margin for error is thinner than almost anywhere else on the California volcano list. 3 GPS receivers and no gas monitoring is not a network that catches subtlety. It happened to be enough this time, because this swarm was in the wrong place and the wrong shape to be magma, and that was legible from the earthquake catalog alone. The next time it might not be. We will be tracking the catalog, and we will tell you the moment any of those 4 signals changes.